As a consequence of that attitude on the part of the great manufacturers like Don Douglas, a very big change had really occurred in the aerospace industry, incredible one. And the change that had come about there is the following. We learned so very much more about alloys since that time. Alloys were being discovered accidentally in the world of metallurgy when I was at Phelps Dodge. The scientists were not looking for a new alloy, but gradually began to learn so much more about the metallurgy itself, really learning that your 18 and 8, these are very important kind of numbers showing up in the stainless steel. 18 and 8, these are proportions of the chromium and the nickel being added to the steel. And these numbers, you can't just make it a little chromier, make it 19 and 8. It doesn't work. The numbers have something to do with the kind of geometry I've been showing you. You can realize this more and more. There's certain phases where things would associate in the right way, so that instead of them looking for just how this happened accidentally, they began to really learn where the periodicity occurred, what kind of numbers would be showing up, and they began to be able to actually design some alloys. This came in with the space technology and the re-entry problems. They suddenly had to have materials to do what no materials they knew of could ever do. Kind of heats that you're going to come to. There was problem after problem. There was absolutely nothing known that could ever get to those limits. So then they began to literally design, by going back to the chemistry and so forth, seeing what might possibly in some of these curves get there, and they began themselves literally designing the right metals, getting the right numbers. Well, this is a very great advance in its own right. So then they began to realize there was no, as you got into these rarer and rarer metals, there was no point in trying to make wire bar and trying to make angle irons and so forth for nobody's ever going to use angle irons out of titanium, whatever it may be to say. So that they began then doing something fascinating. They began developing a set of tools where they would make the end product instantly with the tool. They'd make just enough of that alloy, and this molten state, whatever it was, it would go into the end shape instantly. This is very, not been cut out of any kind of way. This is quite a transition from the exploitation of the mine, that has something to exploit so you get out some shapes that people are going to buy, to really then going after doing the right thing for the right reason. Because you get in that space technology, the airspace down, as far as the aircraft engineer goes, the design of that airplane, he's not interested in making money whatsoever. All he wants is that plane is absolutely safe to fly and do the most for the least. It is a self-policing kind of activity. And so I found that this new one of making the exact, learning so much about production, learning so much about behaviors of atoms, really learning then how you make tools so you could make the end product in approximately this one, having no waste whatsoever. You might have to machine it some more from there on as you got the right form, but we get into all kinds of things like impact extrusion. You get a shape where you have a metal in it and it's in the container the right shape, and just hit it so hard that the thing just extrudes inside in the right shape. There are all kinds of new techniques that came along in production engineering. Now, in relation to what I've been telling you about before, the going from the very stupid kind of a viewpoint of tooling up years ahead of the Detroit world to make money over into the airplane world where they were doing things right, because the thing was to make the plane fly and have the man come home. The thing that came in there that made possible swift tooling was the phenomena tin. Did I go through tin history with you before? Don't think so. I did mention to you that the oldest known history of any metal is the tin history kept by the Phoenicians, and how this became with the great Roman Empire going to England, and there's very much of that Roman world that went on. I learned as I go to England more and more, realize how really long the the Roman world went on in England. It's a very extraordinary matter. And it wasn't just an invasion at all. I mean, it was really a way of life there for a long, great number of generations. And the tin got exhausted in England. Because everybody identified England with tin, and the English then represented the best kind of an unsinkable flagship for the reconditioning of ships in the great runs. It became really then one of the ships that went out of England began to discover that there was a lot of tin in the Malay Straits. There still is. It's one of the great tin sources today. Later on, tin is discovered in Bolivia, and much later in Tanganyika. Those are the main places of tin today around the world. There are not very many of them. There's none within the United States, neither in Alaska nor United States proper. There's some tin in Mexico, and the Mexicans make quite a little with tin. Tin is equally expensive to silver, but you'll find quite a little tin work in Mexico. Now, the tin had a very extraordinary history. First, as men then discovered that the water wheel, and that they then learning that they could possibly get to use from the spinning wheels that the woman had developed, and just a thread making it, and then getting into weaving and so forth. Get there where they could manufacture it from, they could really set up machinery to do that. And you could get the spindles going around, and you do all kinds of tricks of developing the cotton thread and so forth. So we have, using a water wheel, and you can make a waterfall very readily, as the miller had learned to do. And then they found with a great big driving wheel on the fasten the water wheel, then they could have the strap, a belt, go up into the factory to another enormous wheel, a good wide pulley, which the strap, then the friction it made to drive it, all right. Then these are connected, they brought power into your building. Then they had shafts, shaft hangers all running around those factories, and overhead shafts going everywhere with pulleys on them. They're all going around, and all being driven from the water power. Then they placed the machines on the different floors of the factory below the shafting, and from the pulley up above that machine, they then had strapping coming down to a driving pulley on the machine. And they had ways then of getting a double pulley, so you had a rod control. You could move the belt off or onto the drive pulley, so you could shut off your machine when you wanted to. Anyway, the old factory buildings began, the foundations would change, they would sag, and one reason or another, the shafting would get out of alignment. The bearings for all the shafting and all those mills went through, it was a box, and inside that box was called Babbitt metal, but it was tin. And tin has a very low melting point, so that when the bearing begins to really scrape and so forth, instead of tearing your drive shaft, it simply would melt, really sort of like running in butter, and it worked pretty well. So that tin made possible getting the wheels going of production of man. Had a very big part. This was going on in my first jobs, and I got out of Harvard, my first cotton mill, where I was learning to be a millwright and machine fitter, the English called it. And I learned then to get up each one of these type of machines, and I'm deeply familiar then with those functions of tin. Tin had a lot of other very nice functions of soldering, being able to make lampshades, little wire, all kinds of things people could put together with a solder, low melting point. Then it got to be very important with electronics, because it had a solder there to make a really good connection so it wouldn't oxidize. And they have that tin, everybody pretty familiar with that tin was, and the tin, it was found, could be flowed very thinly on the surface, thin sheet steel. So tin cans came in, and tin cans made possible preserving the foods, hermetically sealed. And this is, again, just a World War I type kind of thing. And we had suddenly foods that used to rot, was suddenly reaching people any distance away. Very extraordinary new capability of man. this began to take people away from the farms, and tin had many, many very powerful functions in changing the pattern of man on the planet. But then I ask engineers today, if anybody tell me where tin is, and I ask you, for instance, are any of you familiar where tin is? What's tin being used for right now? I found approximately none of them know. And I found it a very fascinating matter then that after World War I, ball bearings came along, and so much better than these Babbitt motors. It came right out. Then we learned to have individual electric motors on each machine with this ball bearing, so tin was absolutely not wanted anymore in that game. Then began to learn all other kinds of tricks. There were kinds of plastic coatings you could put on the metal cheaper than the tin. Tin was expensive metal. So that we stopped tinning bathtubs and all those kind of things that used to go on, and we suddenly, where did the tin go to? I said there's no tin mines in the United States. It's only in Mexico, and not the very small ones. They're not worth really talking about. And what happened was that during World War II, what the Germans and the English both learned was that the way you could make quick changes in design, particularly in wing forms and things like that, and fuselage, great big parts that need to be done in a hurry. We have something called a drop hammer, and the drop hammer is almost like a guillotine, but the man can control, have it lift really quite rapidly and come down, pounding on the lower mandrel. We have them. And a material was developed called Kirksite for the inventor, and the Kirksite is primarily tin. And tin is such a low melting point that it's very easy. If you want some, you can get very little heat in a little time, and you got it melted for you. And what happened was when they designed a new part for a wing form, then the designing engineer got in his pattern man, and the pattern man, and many really men, craftsmen like sculptors, they could make a clay marble very quickly, just a really beautiful form, put the calipers on it just right. Then they made a quick plaster cast, and from the plaster cast, they then made this Kirksite casting, where you make a bronze and so forth. And they made only the female form, and then they made the male form by casting it into the female. But the female being made, they then could also change the design and smooth it up, because tin, you could scrape it so readily. It was extremely easy to scrape, really easier than wood, and it held its shape so beautifully. So you could dress it lovely. So you could get the female all dressed up very fast, and then cast the male in it with a powdering compound, and suddenly had, within 3 and 4 hours after engineer finished the design, you could have these dies made, and they might be size of this table, big things, and the big drop hammers were quite wide stanch, so that you could get something big in there like that. So that was a male. They put in the aluminum, and the drop hammer man learned how to. He was a hammer man before. He learns how to. He could move it just a little in there, and he'd take a few passing like that, and suddenly there's your shape all nicely dressed out. The tin being soft enough to help allow those atoms really spread themselves. Such a tool is good for about 100 parts, and then it's all through. You have to make it over again. So this is called soft tooling. Anyway, this Kirksite then did make possible swift change in the design of the aeronautical parts, the ship's skins, and really other parts, but primarily that. As a consequence, I'll tell you that the largest tin mines in the world today are out back of the airplane plants of America. You get out and go find anyone, say like Burbank and Lockheed. You think it's sort of a graveyard out there. These forms like gravestones, sort of strange forms and things like that. These great hunks of tin, and they can be melted up just like that. So the ones that meet, this is the most beautiful picture of the New World. A country that has no tin mines. The largest mine in the world is above grade, ready to be melted right up, and makes possible change, swift change. Think what powerful things I'm really telling you. So when we have just economists looking at world of things as an incredible Rome, not understanding anything I'm saying to you, not understanding, there's no book, there's no paragraph or sentence in a book in economics about doing more with less. So it's been held really as a classified way of looking at things. The economists mustn't talk about that. The politicians want. In fact, the economist wouldn't know what he's talking about anyway. He doesn't have that. He doesn't have really any sense about these metals and performance and efficiencies. So the economist just looks at the last tool that ever made that thing. That's what he says. He starts from there, and it's always going to take that much. Now, I hope I've really said enough about evolution in design. So design engineering, I'll tell you, things are very different again from where they were, what Don Douglas did there. So this switch is going on very, very rapidly. And to be really competent in playing world game, you have to be really deeply aware of all this kind of facility. I developed something else which is going to be appropriate to talking about the Wichita House and then the other one which will come up next. That is, back in by beginning with the Dymaxion House, I started something I call the universal requirements of a dwelling advantage or a shelter advantage. And this universal requirements dwelling, I said, I'm going to have to think about, I'm going to try to do something on behalf of human beings, giving them some controls of their life. So we're talking about an environment control. I said, environment, later on, a few years ago, I did this with Sonny Applewhite. I wrote a little poem about it, but this way I looked at it back in 1920. I said, environment to each must be all it is, excepting me. Universe, in turn, must be all that is, including me. The only difference between environment and universe is me, the observer. And environment, this universe, is all in motion. It's utterly dynamic. There are no things. Physicists have found no things. They've found only events in pure principle. So all the environment is a set of events of different frequencies and magnitudes. I saw then that everything that can happen to you, I'm going to try to be competent in designing on your behalf. I'd like to be comprehensive and anticipatory on your behalf, the needs you're going to have. You're very innocent, young, and so forth. I just want to be sure that your things are, that I can turn the experience of others through history to your advantage without in any way impeding you. What can I do on behalf of my fellow man without trespassing on them? That has to be very important. So I said, I'll get that out of the way, and then I'll come back to these environmental events. I said, if I suddenly jumped up and ran over and grabbed you like that and said, what are you doing? I saw that the piece of the ceiling is falling, and I don't have time to put my words. I just run and grab you, and this goes wham, and they say, boy, obviously if I hadn't pulled you, and I didn't really have time to get my words right, I just pulled you out of the way, and it goes wham, you'd been killed. So somebody said, I wish you hadn't done that. I wanted to die. I said, I didn't know you wanted to die. But that, you're going to have to exercise that option. I can't guess that you want to die. So I do not consider myself having trespass on you if I give you the option whether you're going to do the dying. So when I see that things are going to destroy people that they don't see that's going to destroy them, if I do something about it, I don't think I'm trespassing on it. Then I began to realize that human beings have all kinds of processes, that they're really quite unaware of their chemistry and their processes, but the processes are going to take up a lot of their life. So I said each human being has a capital which is the total amount of days of their life. And I do not think I'm trespassing on you if I then anticipate some of your copings with the processes and do things that it's just repetitive, and I save you having to do that repetitive thing. This is simply going to give you a few more days or hours of your life. But anyway, then that I can give people more hours of life, I assume that I'm not really trespassing. So I see then there are these things they don't know are going to happen. They're not familiar with diseases. They don't realize that this thing will infect them, so forth. But I do. Therefore, I have the responsibility of dealing with these things that are going to affect their lives that they didn't know were going to. Now, this means then, I saw then that all the things that happen to human beings originate either in microcosm or macrocosm. They happen to them from outside themselves or from inside themselves. So that gave me some pretty good ideas. I began to see that I can sort out, and this is, and I really did this before I got into the discovering my tetrahedron, you know, getting what is called a thinkable set out of universe. This was probably the beginnings of my tenure to sort out my mathematics in the right way. But I came just dealing the environment on behalf of the human being. I saw then that I could really begin to get things into a set of very important categories. So the things that are going to happen to you from outside you, and things inside. The ones that are going to happen to you outside that you don't know about, and the ones that you do know about. And you'll want to do something possibly to do so. I would like you then to, not going to ever try to insulate you. I'm going to try to give you an environmental control that, we did mention this earlier, that it's going to rain and you can't drink all the water, so you've got to get the water in a holding pattern to valve into your presence and the magnitudes and frequencies that coincide with the human metabolic processes. So that what we have is sort of an environmental sieve that lets through what you want when you want it. The sieve being sort of angular valves. So you have different sized sieves with different kinds of occasions, and you have ways of not insulating or stopping anything, but in some way to intercept in a profitable, favorable manner anything that does happen and to shunt it into its right position. So the energy can be used whatever is appropriate. So then I came to then the things that happen to you that are subjective and things that you could do objectively. And I began to find these things sorting themselves out more and more and more. And there were things that went on outside of you that you were too familiar with to notice anymore. You're so used to that tree being there and so forth, and you don't realize that as it grows, the roots are getting bigger, and suddenly a sidewalk comes up because the roots broken in. Otherwise, there are things that are overlooked that are going on that could be anticipated, that we know that roots do get bigger and so forth. I saw there's a great deal in the design that the more we think about things, there's things that I really can anticipate on your behalf that are not trespassing, and the test is always how to get you more of your life which you can invest in your own preferred way. Now, I advise you all to look at the universal requirements. We have that published in a number of my books, and it's something else, universal requirements, and I continually improve that, and that brings you into the production engineering and into the service industry to maintain and the removal of the product and getting into the service industry. I think you'll be really quite surprised to get universal requirements, because having the kind of experience that I'm telling you about, I've had that list all those years, and I, from time to time, continue to try and improve it. And it's really finally gotten to be quite worthwhile. When I first started in 1927 on this, I said, if I'm going to do things on behalf of my fellow men, what are all the things that can happen to my friends? So I said, well, the first thing you do is start making a list of anything you remember. I said, I'm afraid this list is going to be very big, but I better start in. And I was surprised that I could only work on it for about a week or so, and I couldn't think anything more. People look at you in an unfriendly way, and somebody throws a stone at you, and there are all the things like that you can think about. So I started writing them all down. So I say, after a couple of weeks, I couldn't think anything more that happens to you. Then in 1929, I was having lunch with, this is the year of the great crash, with some architectural and engineering editors, architectural and engineering magazines in New York. They were the leading magazines, and these were their leading editors. And the crash was there. It had already occurred, and they were great, all building had stopped pretty much. And these editors were very interested that I had a list, a checklist of all the problems that designers must cope with. It was good to have such a checklist. They liked the idea, and so we developed at that time a little association. We called it the Structural Study Associates, and they used to come to my place down in Greenwich Village weekly to meet and talk about structural study problems. They were quite taken with my general approach that I'd taken in 1927 about the environment, etc., etc. So at the beginnings of all our meetings, people would say, do you have any more items you can add to the list of things that can happen to you, that we have to cope with. They added a few, and then finally got to it, nobody's adding anything more, so it was decided we ought to publish it. So I published it in Shelter magazine here in Philadelphia in 1930. And once something is published, again, this is something strange, because there is something mysterious about getting into print. Printing machines belong to human vanity. You're getting to talk to a lot of people. You could be trespassing and doing something wrong by using the capability to speak. And so I think I personally find it very mysterious if the system you live in, your things really do get into print. And how it was, once it was in print, I felt I didn't have the responsibility of having to remember it anymore quite the way it was. There's lots of copies of this out. A lot of people know about this. So I was very surprised when I happened to look at it a few months later, and in my file, and the sheets when I've been working on it, the printed sheets were there, and I suddenly looked at this thing with new eyes. I said, this list is really quite crazy, because I had mosquitoes alongside a tornado. I said, they're really quite incompatible. I think I ought to take this list and sort it out all over again in the order of relative severity of its effect on the humans. I don't know why I hadn't thought about that before, but I hadn't. You can understand how I hadn't actually. The way I came at it, I need to have a list. So I then said, I'm going to then try to get each of these in the category. And sure enough, I found that I began to put each of my items into a file cover, regular letter file covers. I had them labeled there. One was called the only item could go in there were novae, the explosion of stars. It was very large. And I call this, eonistic or something like that. And then it came to epochal, something enormous, and then something word enormous, and then something pretty big, and then not so big, and so forth, and down to finally to innocuous. So I started sorting the things in these envelopes, and sure enough, there wasn't. Every one of them had something to do with man or something to do with severity, so they all had an envelope they go into. So within their envelopes, and then began to see, is one of these a little more than another? So making little strips, I was able to sort them. Sure enough, they really did range out. Every single one of them was easily, this one is just a little more severe than that one. You can really think about whether hearing trouble versus scratching your face, whatever, you can find out. So I ranked them all, and when they were finished, the most extraordinary thing happened. Do you remember earlier I gave you the definition of science by Sir James Jeans as the attempt to set in order the facts of experience? It was not until I did what I just did that I suddenly realized what extraordinary statement he had made, because these were experiences, and I suddenly sorted out the facts of experience into relative order of magnitude. When it was done, absolutely clearly, the most severe was the least frequent. That this was absolutely pure quantum mechanics of the universe. When the universe does, then you always she has her energy. You don't make energy, there's the energy. So anything she wants to do, she can do a few big ones very infrequently, or a whole lot of little ones very frequently. That's the way the universe is run. That is quantum mechanics. Always adds up to what have you. So I saw then, this was pure quantum mechanics. The big ones are the least frequent. And quite clearly, mosquitoes are much more frequent than tornadoes. So, boy, I didn't have to have the name tornado or mosquito anymore. They could have a number on it. I said, this is an incredible kind of a capability of a designer to have, because part of my design was also then total responsibility, and recognizing the rates of change of design, I would always have specific longevity. How long did I expect this one to be valid? Not something you're trying to sell and get rid of, something you're being responsible for. So I'm going to design this for 5 years. Therefore, this is something that only happens every 300 years. I probably won't have to bother about it. I wouldn't know how to make a house novae proof. So I don't try. But I see the things that I can do quite well. because you and I wouldn't be around anyway if it were Nova. So I saw what I was really responsible for. It was pretty easy with that list then to suddenly say, what is the total amount of time I really am responsible for? Okay. Now, that is universal requirements. I say, if you look at it today, it's gone on and been rewritten time and again to actually incorporate what I've learned a little more from each of my experiences, getting something going, reduction of practice, working with society to be an absolute reality, and how you then, it's possible. You can see how I would like to get things withdrawn and get the fresh thing coming. So now we're going to look at some pictures, and these will be, the first one is that's what I call the grain bin house of the Butler Manufacturing Company in Kansas City, and that's a picture taken in 1940. As World War, this is 1940, you see, I'd just done, to think about, I'd left Fortune in 40. This is the thing I did next after Fortune. And I had been traveling in the Midwest in southern Illinois and so forth with my friend Christopher Morley, who was a great writer. And I saw these grain bins of the Butler Manufacturing Company, and the grain bins were all around. They're corrugated steel, horizontally corrugated sheets that are bolted together, and on the top they had a conic roof. And part of the great New Deal coming in and trying to rehabilitate farms as well as mortgages and so forth was that they began then to credit the farmer with wheat, so grains could be harvested and the government would loan, or they would pay the people for the harvest that's put in the grain bins. So grain bins were where the little farmer could cash in, and the government would hold and stabilize the price to really look out for him. Grain bins then were enormously proliferated, and this Butler Manufacturing in Kansas City had the best grain bin. There was nothing to touch it. I got to know the old man, Mr. Norquist, who was an old Swede who produced the first one, good metal worker, sheet metal worker. And then he became then the president of the company. They had a factory in Galesburg, Illinois, and another factory in Kansas City, over fairly close towards the area where Harry Newman lived there, Harry Newman, and Harry Truman. I worked for 2 years with Butler getting this thing fixed up, because I saw in that sheet steel corrugated, getting a most wonderful enclosure, but not something you could live inside. The moisture, the precipitation things were not good. If it were properly insulated, and if it had the right kind of a roof, because it was an open, just a conic top, corrugated, and airs came in, insects had come in, and so forth. And I saw that if I had some windows in the grain bin and so forth, that I really could convert it into a little dwelling device that I felt, with the war coming, could be extremely important. And so I kept telling Chris Morris, we were on an interesting mission of his, going down to the Mississippi River to a little tiny town on Mississippi. Chris was visiting Knox College in southern Illinois, and the visiting English department, giving a lecture there, and Ralph Sargent, who's been the head of the English department at Harvard for many years, was the English professor at the time. We went down to see a little town on the Mississippi that Chris Morley had been following the records of Edgar Allan Poe and so forth, and he found that Edgar Allan Poe had been going down the east coast of the United States and got down to Louisiana, was going to go up the Mississippi, and found that Edgar Allan Poe there was a man who owned the first printing press on the Mississippi, a little town. I was on the east bank of the Mississippi, not far across from Hannibal, and he had invited Edgar Allan Poe to come out and be his editor to start a press on the Mississippi there, just a little bit below Nauvoo, where the great colony had been of the Mormons and so forth. And so Edgar Allan Poe was on his way, and he never got out of New Orleans. I'm sorry to say he also drank quite heavily, but at any rate, I don't know. I'm not sorry about anything. Everything's great. He had a good time there. Anyway, Chris Morley had a hunch. He'd like to go and see this press, and he found that the press was still there, and the family of the man who had owned it was still there, and he asked if he could go up and look in their attic. Chris made friends very readily with people, and he went up in the attic, and he found all the correspondence of Edgar Allan Poe of this man who owned the printing press about arranging to come out, so it was an enormous, great find. Well, just at that time, Chris Morley, who had also, he'd been brought up at Haverford, and he was therefore a Philadelphian and main line, and he and his three brothers, each one of them became the Rhodes Scholars from Pennsylvania and went to Oxford and Cambridge. And Chris's father was president of Haverford. So I used to see a lot. Chris and I used to go down to Haverford quite a lot. At any rate, Chris at that time wrote a book called Kitty Foyle, which was about the white-collar girl in Philadelphia. And it was extraordinarily well done book. It became very, very popular. And the first time Chris, with 45 titles, ever really made a large amount of money. And it then went into a moving picture. And if you haven't read Kitty Foyle, and being Philadelphia, you might really find it extremely amusing. Really very pleasant book. And so he made some money, and Chris Morley said to me, I think Kitty Foyle would like to have you go out to Kansas City and see the president of the Butler Manufacturing, because you've been telling me about all the things, how you might be able to make some nice low-cost shelters, because obviously they don't cost very much money. They're really being stamped out, and so he said, I said, Kitty Foyle would like to pay you a fare to get out to Kansas City and back. I was very penniless at the moment, I'll show you. So that was great. And I did go out, and I met old Mr. Norquist, the president of the Butler Company, and he liked me very much. He loved the idea of using grain bins for houses. So he cooperated very much. I spent 2 years getting this thing really going, putting different kind of roof, a compound curvature roof. I got to put a dome on it rather than a cone, because a dome is simple curvature, a cone is simple curvature, compound curvature, very much great strength. So I worked out ways of very simple press work to be done in their shop to make the compound curvature. Then, this is when I said, we now will be having housing and building with so relatively little material, that instead of building from the bottom up, which is the way buildings have always been built, I think I can, because it's circular and will have structural stiffness of compound curvature, I think I could then build this from the top down, because I see one of the ways in which one of my responsibilities as comprehensive designer is not to have a lot of people killed. In 1927, I started the Dymaxion House. The most dangerous industry in the world was the building industry, by far. And the second most dangerous thing that happened in accidents was in bathtubs. It's interesting. Number one is the building industry. So to such a thing as bathtubs and then building is something I really wanted to cope with. I saw no reason then for people having to go on scaffolding. So I think I told the Butler engineers I was going to want a secret place to put this up. They found this place behind one of the other factories there where nobody could see, and I then did assemble. I put up a mast first. Then there was an assembly ring where all the roof pieces came together, and this was going to be used later on to mount a ventilator. So I put my assembly ring in the ground, put my mast through it, and then stayed my mast. Then I could had pulleys and so forth with a block and fall to get with a sling to my ring, and I could lift the ring up. So I pull the ring up at the good height for the people to work on it while they brought the roof pieces together. And then I keep hoisting it up and keep adding on the ground. So finally I got it up where there was one more ring to be put on, what you can see here, but at any rate, I had it up off the ground by quite a little. Later on, I was going to let this down, and what I had done was to build a dig a trench, a circular trench, which is very easy to strike a circle, and then take the earth out of it and put it up and put it into the center of the circle, so that you would get a little plateau above the water, any sort of drainage problem. And then I got a bunch of brick, and enough to lay the brick side by side with 4 inch this way, flat, and make a complete ring where the grain bin could sit down on that ring of bricks, act like little snowshoes, and distribute the load. And then to find some way of fastening the grain bin down tightly. And it did have, the bottom of the grain bin had a turned angular skirt like this, so that with holes in it, so you could fasten it down, staple it down, or to put any kind of stakes you wanted down. So I had in this picture, if you remove me from the picture, please, have then this dome is on its mast and hoisted up, and underneath, inside, there's a pile of sand, which I'm going later on to flatten down evenly inside the brick to act as a base for the floor. And this pile of sand was inside there. I called the engineers and the president of the company and said, would they stop when they came out to lunch and come and see the dome? Which they did. Now, it was August 1940, and it was noontime, and on that day it was well over 100 in the shade. It was a fantastically hot day. Kansas City can be one of the very, very hot spots. And so they came out, and they really were astonished to see a grain bin hung from a mast. They had no idea you could do such a thing. It's really, once you see something like that, it looks pretty easy, but it just not occurred to them. They'd always been going up on ladders and to get some of them built really quite high, and the ladder work was really very uncomfortable. Suddenly saw you could do this mast game. So the president of the company said, I'm going to go inside. You could not touch the metal with your hand. It would absolutely burn you. There was on one side there was where the doorway is going to be that you go in, and so he went through the door, and he called out to everybody. He said, hey, it's air conditioning in here. He said, just like the Kansas City Club. And so everybody thought he was kidding, and went in, and absolutely nice. It was really cold inside, truly cold, and over 100 in the shade, and cold. And everybody wondered what's going on here, so they lit cigarettes to see if we could see what happened to the air. And sure enough, most of it was extraordinary thing, the air was coming down at the center. There was an opening, you see, around the great big ring, 3.5, 40-inch ring diameter, and the air was coming just down like that and going out underneath the edge of the dome. So you see the smoke would come right down and go right out. This is then where I'm getting into very important aerodynamics of buildings, where I found that we have concave and convex. Now, I've spoken about concave and convex not being the same. The radiation impinging on the convex is diffused, and the radiation impinging on the concave is concentrated. So the sun is shining on a convex surface, and the convex surface then diffuses the sun radiation into the atmosphere, and this atmosphere is then heated. And the heated atmosphere means the molecules become a little more active, taking up a little more room. There's no confinement of them now, so they take up more room, therefore they weigh less. And therefore they start a thermal, it starts rising, and to take the place of the ones that are rising, air has to rush in from below. Now what was going on here is really a fascinating matter. And I got in this more and more, big pattern studies, that then there's a thermal rising from this thing, and it's then having to get air to satisfy it from all around the base here, rushing in. I found then that if the dome was up like this in the air, there's also with every thermal also a down thermal coming like this. At any rate, the airs were being pulled out from underneath the dome by the operating column, pulled it out. So it's pulling the air in through the hole at the top. Now we have the Bernoulli principle. This is pressure differential. And just go and study a Bernoulli principle in your physics book, and you'll find that we have pitot tube and so forth. With the Bernoulli principle, when you pull the air through a small opening, it takes a good deal of energy doing it, and it takes the energy out of as heat out of the air to do this work of concentrating it. any of you ever flown a light plane, if any of you learn to fly, you'll know as you start learning your flying, as you then coming in for landing, you want to approach the field, you're going to then make a leg. We get to the point where you cut your motor and start your first glide, and then like this and back down. As you cut, where you cut, you have your prop fastened to your engine, so there's not a clutch. And you don't take the key and shut the engine off. What you do is you push the throttle, you simply starve it of gas. And as you do that, then the prop still goes around. The engine is connected to it, so the piston is going up and down like that. And the engine the ship is slowing down, because by the time you make a landing, you want to get where you get the nice stalling speed. So you had to start that slowing down. You then learn that the air being pulled through the carburetor gets pulled through a fine little hole in the needle valve by an enormous pull. And you have to put on what they call carburetor heat. Before you push your throttle back, you put on carburetor heat, where they take all the heat possible from the manifold and concentrate around that carburetor. Because otherwise it'll freeze up with you, because it gets so cold. So that when you're going to make your landing now, you made your glide, and now you're coming in, and suddenly you going to hit some wire. Wire's not high enough, your little engine, no engine. So carburetor heat. This is Bernoulli principle. Pulling air through a small opening makes cold. So what was happening was that this enormous amount of air being pulled out. You can look at the edges there, good and high, and so it's been pulling all out in all those directions, and being pulled through the small opening at the top, and it's absolutely cold down current. Now this was very exciting me to really learn that a building could be an air conditioning machine in its own right, aerodynamically. All my geodesic domes, I then realized this was there, and as I built any of the ones that are large enough, they're going to have really quite large occupancy, and the patrons, like my dome and so forth. But when I tell them about it, I tell you, the air conditioning salesmen are much better than I am, and so they always put in the air conditioning so everybody knows that heat rises inside. Well, don't do this nonsense. So that what they would do was put a fan inside my thing and trying to pull it the other way. It's completely frustrating. What they should try to do. I told my Ghanaian students in the University of Science and Technology in Kumasi about this, and they were really interested. And they didn't like the idea of that air conditioning salesman anyway, so that they also had this great Volta Dam and all this big electricity going to be, and enormous amounts of bauxite. So in Ghana you'll be able to make aluminum. So I said, let's get into a big aluminum dome. So we designed a really beautiful big aluminum dome. And it took them a couple of years to produce it, but to make the chilling machine. This is a picture of it. It's unusually lovely. To me, it's the most beautiful of all these geodesic domes that have ever been built. And this is made first, they worked 2 years on the mathematics. Is the 12 frequency truncatable into the same mathematics they used for the 72-footer I told you about of tensegrity at SIU. And they had plenty of big openings at the bottom, you see, but putting lovely little hoods for the rain. And they had just a nice small opening at the top. This was put up in the fairgrounds at Accra. The government decided they'd like to have it there, and it went through several international shows. And sure enough, minutes up, all the Ghanaians called it the chilling machine. And the hotter the sunshine, the colder it is in there. It's just a lovely thing. It's ideal for the tropics. I'm astonished how little listening to I get about what I'm saying to you, though, and how people keep right on. So talk about our energy needs. This be one of the typical things you really do a lot. It doesn't do it for you at nights. That's one reason to say what you're going to do in the night time and so forth. But the point is you have it good and cool during the sunny times. It's going to stay fairly cool. But we do have hot nights, and there are other things you're going to have to do then. But the point is that it works while the sun is shining. Anyway, I learned about that from the Wichita, for the Kansas City 1940 deal. And also learned a whole lot more, which was that I could hoist buildings on the mast, and I've used that ever since. It's been extremely, extremely useful. Next picture, please. back to the grain bin. This is down in Washington, D.C. There's a little called Haynes Point. It runs down, but there's the Potomac River coming down, and this Haynes Point doubles back and makes a great harbor that was the Washington Harbor. Such harbors they had. The steamers that used to go down to Norfolk came to this little harbor. So Haynes Point is really an island, almost an island in the Potomac, and it's pretty close to where the airport. You cross the bridge over Haynes Point and then turn to the left, in no time you're at the airport, the Washington Airport. And this is they used to have on the Haynes Point a tourist camp. This is before World War II. This is picture 1940. And there are a great many people who, the representatives in Washington, like the people from home to come there and see them at work in Washington, easy to help get themselves re-elected. And so they had this great tourist park on Haynes Point. And they had, so people could come in buses and sure enough, spraying the graduating class would win the right to go in the bus all the way across the country to Washington and see Washington. So the park had all kinds of bathing facilities and little houses where people could live in dormitories and things. And the housing people in Washington, with the war coming, became terribly interested in this grain bin, and they asked me if I'd bring one to Washington and put it up at Haynes Park. So it's over there in the corner of Haynes Park, and I see that three people, there's myself out in front there, but Wally Saunders, who worked with me on the design, wonderful architect at University of Michigan, who's now dead, and his wife Carol. This park on Haynes Point, and they had, so people could come in buses and sure enough, spraying the graduating class would win the right to go in the bus all the way across the country to Washington and see Washington. So the park had all kinds of bathing facilities and little houses where people could live in dormitories and things. And the housing people in Washington, with the war coming, became terribly interested in this grain bin, and they asked me if I'd bring one to Washington and put it up at Haynes Park. So it's over there in the corner of Haynes Park, and I see that three people, there's myself out in front there, but Wally Saunders, who worked with me on the design, wonderful architect at University of Michigan, who's now dead, and his wife Carol. And you can see the car in the background, get a little sense of that's a 1940 car there. So that the grain bin really worked like a dream. And we're able to produce this whole thing for $315. And inside, next picture, it had lovely cooling door on it and screen door. And it had curtains, which like theater curtains could be pulled up, a chain at the bottom so it weighted and once come down to the center. And then theater curtains, bring in a circle, as a semicircle, pull it up. You just let go of the cord and the whole thing would shoot to the center where you see that one on the lower right-hand side going in. And we had the walls were everywhere. The inside, the beautiful insulation, used fiberglass insulation in them, and wall board holding the fiberglass in there. And the runners that held the wall board, the vertical runners, had keyholes in them so that you could put shelves or anything like that you wanted. And we had a ring going around, first what they call plug-in strips, wire plug-in strips going completely around, so you could plug wire and anything, electrical wire in and come down to any fixture you had. The president of Sears Roebuck was a friend of Mr. Norquist, this old Swede who owned the Butler Company, and he helped me a great deal. And we got up a package in the Sears Roebuck of a kerosene icebox, a kerosene stove. I developed a toilet, which was just a little cylinder, using a septic tank, which was a tank in itself, and just extending that size with the same corrugated metal and a little top on it, and had a partition in, so there was a shower here and the seat there and a little wash basin, all on top of the septic tank, so that did its work. And there was a water tank for the water up in the top of the little cylinder itself. So it shifted a horizontal cylinder up and fastened onto the little dome here. The whole dome cost $315. The total, the Sears Roebuck package included two roll-away, what we'd call the chaise lounge, you can lie down flat, two roll-away beds, and six kind of a drugstore aluminum metal tube chairs and tables, really fairly standard kind of plastic top table. The whole thing with the bathroom and all came to about $700. It was an 18-foot diameter, really extremely comfortable. Wally Saunders and his wife lived there for quite a while, just really checking out, because he was a very good architect, very good housekeeper, and they really found it extremely good living. Then the flooring in itself, you might say, how did you do that? So I wanted to keep that very simple. I told you about then filling it with thick sand inside the bricks. And I wanted to be up above any water table, and I developed the drainage thing that I told you to get some height by the dirt you took out of the trench itself. And then I put down corrugated, again, galvanized steel sheets which overlapped, the corrugation overlapped each other like this, cut them into sections which made a circle. You made them in a triangular section, then dressed them a little more, the curvature. So not really, no real waste of the sheets. I was able then to have the curvature ones of this wall, and they keep adding, and they keep overlapping each other. So there was a continuous metal like that, and that sat on the sand. And then on top of it, I put at right angles precessionally to the corrugation and the joints of the corrugated sheets, I put soft insulating masonite, half-inch, ran that way, and then turning at 90 degrees again the joint around the masonite hard surface panel. And there's an interesting thing about the masonite with a hard surface polish on one side and on the other, is it always wants to bow upwardly, so that by having it on the floor, it laid absolutely flat. It never wanted to curl up towards you. And so I was able then to have completely dry floor, just laying these things the way I said to you. Nothing fastening down. The whole thing held down just absolutely superbly. And we found it one most attractive. There was a springiness of the metal going down into the sand. It was a very, very comfortable floor. So it was a completely demountable affair. We developed these with the housing authority and the war people. All the departments in Washington were terribly interested in something you might really call, this is the DDU, Dymaxion Deployment Unit. But in New York, at the time I was doing this, there were a number of Scots, and these Scots were, some of them were just visiting there and so forth, but the Scot great landowners had offered to England to use the Scot moors for, with the bombing expecting was going to occur in England. They'd like to have a place where people could deploy, and they wanted some kind of shelter, so they liked this. Now, the actual designing was done for them, and they were the critics of as whether it was valid. When suddenly the war did break and England was in, they found that the highest priority was steel. Simply any steel they could get from America had to go in the armaments. So that was not available for this. I was able to get quite a few things done. The windows, the first time plexiglass or the acrylics were ever used for a window, the Air Force had all of it absolutely tied up. So I had to go after my friends in one way or another and wangle to get some of it. So the windows on this thing, the first time a building ever had acrylic windows. And they had little hoods over them too. Worked out some really nice kind of mass production windows and screenings and so forth like that. But that you could do such a thing for such a price seemed amazing. What happened was that they were used, the defense, National Defense used them at what used to be called the Signal Corps. Then there came that was given up altogether. But the first radar work was being done. All the research work on the radar on the coast of New Jersey up here, and they needed a number of little shacks for doing all kinds of radar studies of boats on the Atlantic. So I put those up for them all over the place. Then suddenly the war was really on, and the United States used them for the Russians, then were their allies, and to give the Russians airplanes. They sent ships with airplanes into the Persian Gulf and up. So that's where we're getting to the oil kind of game going on. The northern end of the Gulf, they had the unloading. This is where we made the flyaway deliveries of planes to the Russians. So the Russians and Americans have lived in these things. Like General Electric got out an air conditioning unit to be inside them. It's very hot. It was very hot down there in Arabia, and so $125 air conditioning was added. So things still was under $1,000. Really a very good home. So all the crews that put together all those airplanes for that lived in those dogs, and they were used fairly generally for radar-controlled shacks. Well, this piques me in many ways to realize that you could have so very much for so little. This next picture would come into then what happened to the series of buildings in the. Oh no! Here's my bathroom. The bathroom, as remember, was a late Phelps Dodge development. Did I tell you that? And I did use copper to do it. But may I have those bathroom pictures, please? This is the first one I made, and then I perfected it very, very much. Next picture. This is the second model, and the top halves have been taken off. On the left-hand side, you come in the first one, you can see where the seat is, the toilet seat, and on the right is your wash basin, and you step on a step through a doorway into the top, and we had Venetian blind forms to keep so the water would not come out in the outer room at all, but you could have your shower and everything was inside that second part. The tub itself, what I learned about the danger of tubs was that all those accidents. Number one, the old-fashioned tubs up in legs, they were different height. As your legs came out, the tendency was to tip over, fall like that, anyway, going either direction. And so I had then a step. If you're going in there, you'll see a built-in step in the wall. All this is then actually a formed affair, like forming an airplane wing, you understand, stamping an automobile part. There's a step with a cork top on it, and the door, when you take hold of the sides of the door, the handles on the door, you step into the bathtub. You just could not be more secure. And the height of that step and the height of the tub were exactly the same. So you felt very comfortable going. But because I had the tub elevated, considerable height with the step, then the housewife could lean in there very easily to wash it when she's standing on the floor. So it was extremely easy to clean tub. Now, everything I did in this room, I like to have my own figure out of the way so that I can talk more about it. I found one of the things that would be very desirable and with a wash basin would be that you could also wash the babies in it. It could become a really very safe kind of a little wash basin. But you don't want spigots sticking out in the wash basin and all kinds of things around. They're really very dangerous in relation to the baby in it. And I've also felt they're really quite bad for hitting your own head and so forth. So that this wash basin, my pipes came up on the inside the rail where you stand up against the front rail there, the pipe's inside there, and there's a hole, a nozzle, but just fed into the wall on the side, and the water goes away from you into the tub. Instead of having the water come up your cuffs like that, as you stand in front of it, as you turn on the water goes away from you. Of course, it has the hot and cold mixing valve so that it comes out just as you want. I found how to make very much better nozzles, really a lovely kind of a stream, and so water was going away from you, and here's suddenly, and I made the size of a really good tub to bathe a baby in, the largest size baby you'd want to ever put in. So it was very, very comfortable. Nothing sticking out. There was no sharp things. All absolute smooth curves, and as I say, no spigots or anything like that. And the water came out just on the same side towards you, above the spigot where they came in. So everything worked very nice. Now, I had between the two rooms, so that each one of these were made the size of the doorways. If I wanted to get one into an old farmhouse and so forth, and they were 28 inches wide, so they could go through the smallest of doorways. And they went in two sections, each of these oval forms. And the oval forms that I had, the compound curvature, it was a 4-inch radius of the compound curvature, which was extremely neat. And I was able to make up dies where the whole bottom of the bathtub is made of this oval die with a 4-inch compound curvature. The ceiling pieces are made that way, and then the die broke up into separate pieces, and you could make the seat section you see there, or you could make the floor section. All these got pressed, these are part of the pressing, or pressing the inside of the bowl there. So between the two, when there was a saddle, and all the manifold of pipes ran below that saddle between the two, and the top being elevated, then you could dress your bathroom. A total outside dimension was 5 feet by 5 feet, and it could go up in the corner, and wherever pipes were, they could come in underneath the tub through the wall from this side, that side, and come to the main manifold. So it's very easy to hook up. And I then had also between the two of them electric strip heaters, so that it was self-heating, and therefore if it had an old farmhouse, you could have trickle current, so it could not freeze up during the winter and so forth. Then the whole of the drainage of the tub itself was towards that saddle side. The drain was on the side there, very, very gradual. The tub was a really usual tub, maybe 5 feet overall, but there's a very long slant, so the actual bottom's only maybe 3 feet or so. This tub was so large, it's the only tub I've actually floated in. My head's touching here, but body literally floating out like you're on the ocean. It was a beautiful thing to be in. And it was 6 inches wider than the usual tub, so it's very, very comfortable for your arms. I remember when one of the early bathrooms like this was bought by Neutra, used it in a design that they used in a house of a man who was John Nicholas Brown at Fisher's Island, and it is John Nicholas Brown is, I think, 6 feet 6, 7, and his wife is about 6 feet 3. They're both really very big. And they tried these bathrooms. They said the first time they really were ever comfortable in a bathroom. So that even though the whole thing was only 5 by 5, it was extraordinarily comfortable. Say the wash basin was much bigger and more generous than any you ever had. Now, I really did spend 2 years doing nothing but really getting things where they could be really right on this. I said this is why I use in the stainless steel toilet bowl, so that it would not break up if something fell on it, and could have absolute, very correct choke, so I use very little water for the flush out, saving very large amounts. The average American is, every time he just flushes the toilet, may just use it for a little liquid. He's using, we're averaging about 5 gallons to get rid of a pint of same water. Just polluted water, polluting water at that kind of rate. Nonsense kind of thing go in that bathroom. Water being so extraordinarily valuable. We don't know of any other planet with any on it. Sorry. Now, that bathroom between the two, then there's a lot of space where that saddle is, where you step in, where the pipes ran through. And so that near the wash basin and the tub, the two ovals are going away from each other. There's really large space. And I had on the side, as you're standing in front of the wash basin where I'm facing now, and up on your left then, there was a door. And you open the door, because the door was a cabinet, this large space between the two sections. And it's a very big cabinet. It's so big that you could put in a full bucket in the bottom shelf. Then I had that hinge to open this door. There are things you'd like to have in the cabinet, so you open your cabinet because you want something out of it. As you did, the mirrors on the inside of the door, so it opened the mirrors down in front of you in the wash basin, and the shelves are open to get the thing you want, so you're not continually opening and closing, and then when you want, you close the mirror off, and all the room's all nice and neat again. So that it was, in every way, it was designed for the air conditioning. Below the wash basin, you can see a little, on the lower right-hand side there, a little space there. There was a hookup, there was a large ventilator outlet, and the airs came in through the sides of the doorway up near the top. The fresh air was brought in through there and was pulled out by fan below the wash basin, so all the steams and all the smells went down away from you. Now, all I had to do, everything was so complete that we had all the manifold of plumbing, all the wiring, the heating, lighting was all built in, and all you had to do was to hook up to the fresh water, hot water, and the cold water, the waste, and the air vent. That's all you had to do. And so this really got to be a very, very good unit. Now, I had very interesting experiences with this because also, on time of the Dymaxion House, 1927, 28, coming to New York, 1929, there was a man, quite a rich man in New York, and he got quite interested in my Dymaxion House. And he asked me to come give a lecture on it at his house, and Frank Vanderlip. And he invited a lot of people, like Clarence Woolley was the president of American Radiator Standard Sanitary, who he thought would be interested in my house. So he had me give a talk up at his house, and then he had O.N.D. Young, who was president of General Electric at the time. He was a very influential man, and he brought all these influential people to see the house. These people were full of really considerable consternation. The Dymaxion House was a problem poser to these human beings. I had one of my classmates was Fred Ecker, and his father was the president of the Metropolitan Life Insurance Company at the time I designed the Dymaxion House. And I wrote to Fred Ecker, and then I saw him when he came down to New York. I said, the life insurance companies are betting on that people are going to live longer, and people are betting they're going to live shorter. So I think anything that we might design that eliminated accidents and probability of human beings having trouble in the house ought to really then improve the life insurance company's bets, so that I think the Metropolitan Life ought to be tremendously interested in my house. And that did turn out to be the case. Fred Ecker was absolutely excited, loved it. He was one of the young junior officers of the company. His father was president at the time, so he introduced me, then the controller, and then finally met all the officers, and we had a number of very enthusiastic meetings. They're going to back this thing. When suddenly, we got to the board of directors, and turns out that the life insurance companies at that time were only allowed to invest in municipal or federal, municipal, state, or federal bonds, or in mortgages. And so that the Metropolitan Life found all of its capital was in mortgages. And they said, if we let the Dymaxion House get going, it's going to make all our mortgages all the value, so we can't do it. And the board of directors just can't back it. This really was a very frustrating sense that I had about that, but people could see, yes, it's very desirable, and yes, they had all very good business reasons why you wouldn't do it. Anyway, Clarence Woolley, head of Standard Sanitary, became very excited when Frank Vanderlip had me show this thing to him. So he wanted to have something done about those bathrooms and my kitchen and things like that. And so I did then do work for the Standard Sanitary, used to be called the Pierce Foundation, was their research department up in Buffalo. And there I developed what I also had in the earliest patents of this thing. The kitchen and the bathroom plumbings would be back to back, so that you would only have to bring the water to one point. You can understand that was very logical. So that I developed for up in Buffalo in the research department a back-to-back bathroom and kitchen, which had never been done before, and that's become really pretty standard in housing to do such things. Anyway, I made the bathroom in panel forms. I must well tell you this because it's good production and design engineering kind of way. What I did was to develop, in that case, a frame construction where I used tubular just pipes, and you could take a piece of channel iron, it'll nest up against a pipe, a beautiful friction, it's very tight. I made channel iron frames, quadrangular frames, which then sat in between vertical pipes. And as you put it up, then the pipe in place, it was possible then to lock a number of panels. I'm going to a wall side, each one of these panels was about, let's see, there were 3 feet for about 2 feet, so that I'd have, to an 8-foot wall, you might have 4 of them, one above the other, and they were panels which I used sheet metal, and you made a pan, and the pan then would receive a piece of mason or Celotex insulation, would fit neatly in the piece of pan. One of the things that the Standard Sanitary, the plumbing people have a lot of, is ferrous enamel work, beautiful enameling, where they take literally glass and melt it up and melt it onto a surface of steel, and makes a very, very fine surface. So that I learned a great deal about the radius you have to use on your metal, and I'll be able to have it not crack at the edges and things like that. So developed these panels, and they could be lovely colors, and they would fasten into your wall. So, but I could have panels which the panel also turned out to be a wash basin, or the panel could be the seat, so that the walls could spout. You could have interchangeable with just a plain panel, various fixtures that did various things in the bathroom. It really worked out extremely nicely with this back-to-back plumbing manifold behind that wall. So the bathroom fitted in the panel system. Everything fitted very nicely. The bathroom was really very charming looking bathroom, and it was not as full as the bathroom I developed here, all one piece at all, but it began to be part of that, where things were coming off the walls instead of coming off the floor. It was easy to keep the floor nice and clean, at least. The standard sanitary, American Radio Standard Sanitary, suddenly stopped this whole thing, and they just clamped down on me. We must not talk about it, because the plumbers union, which is really is an employers union, because the plumber is a master plumber himself, both employer, but the plumbers union had a national plumbers magazine called The Ladle, for pouring then your lead and so forth for joints. And The Ladle published an article saying that Standard Sanitary, they heard, was working on a bathroom, and they would never install these things, and they're going to stop buying anything from Standard Sanitary. So Standard Sanitary was sickened by this thing, so they must absolutely keep it quiet. And because there'd be really very little work for just installing things very rapidly. Then I told you about Phelps Dodge, and Phelps Dodge having their Phelps Dodge copper products. And I told you then that in Phelps Dodge, I was trying to get things that really help them. So this is a good chance to try out my bathroom, and I'll do it a little better this time. And so I did get out that good bathroom that I told you about, and I found that the president of the National Plumbers Union was also the borough president of the Bronx, and one of the great Franklin Roosevelt supporters. And so they were having an annual banquet of the union in New York, and I asked if I could present my bathroom at the time of the banquet. So they said yes. So I put it up in the dining room, and they were fascinated with it. And I said, I've looked into this matter very thoroughly, and I find that the electrical fixtures people, the electricians, make a great deal of money that you boys do not make, because it's part of the law of America that the land is it, and anything that's fastened to the land belongs to the land. This was incidentally why lunch wagons began. You've seen lots of them. And wonder why they're lunch wagons, because they were brought on wheels, and as long as they go away in the wheels again, they did not belong to the land. And they were able then to get out much fancier equipment that was not then claimed by the landowner. But if you put a bathroom into a house in America, it belongs to the owner if you're renting. So people were not putting bathrooms, so many were renting, they were not putting bathrooms in, because it couldn't belong to the owner, was used to doing that. But the electrical equipment belonged, because it could be taken away, then belonged to the owner. So people bought lots and lots of electrical equipment. So I got into all the figures of the marketing of the electrical equipment, and showing how much the electricians made out. So I said, I now have a bathroom which you as a plumber can sell as a bathroom, get a nice profit on as a bathroom, but you get paid for installing these things. You're going to install many more of them. So at the dinner they decided that was so. So their magazine then published a very laudatory piece about my bathrooms. Suddenly, in Phelps Dodge, the Phelps Dodge copper products people were in great competition with the mining president of Cates. And Cates had backed my bathroom. So that the Phelps Dodge said, our biggest customer is Standard Sanitary, and the Standard Sanitary people didn't know about what I'd done to these plumbers union and so forth. They notified Phelps Dodge that if they kept on with my bathroom, they were going to stop buying copper from Phelps Dodge, so Phelps Dodge dropped it. I had not designed it to be in copper, incidentally. I designed it to be in polyester fiberglass, which was in the laboratories, but at the setting temperatures at that time where you had to have the temperature 200, 300, 400 degrees, not room setting things. So, but I was assuming that we'd get to where you could, so it would be ideal in it. and I had to put a kind of surface on it which was made of antimony and tin. It was a very lovely thing, would not tarnish, wouldn't oxidize. Anyway, I want you to understand the kind of history that you do go through and the interplay you have with the big business and the idea of the money, where people can see the logic of something and support you for a while, and then suddenly turn very sharply because it's putting they're in jeopardy, their incomes and so forth. So now we come then to I've been using a lot of time already, and we haven't actually gotten opening up these pictures of the Wichita House. But if you don't mind, we'll go on a little while, and if it's all right for me to go on for you, okay. We have then, there is Wichita House, and it's called Beech Aircraft, and you'd like to know how I happen to be doing Beech Aircraft. It happened then in the, as I told you, on the Board of Economic Warfare, and we had in Washington for World War II the War Production Board. And the War Production Board was run by start off with by the vice president in charge of manufacturing, General Motors. He knew the most about production. And the War Production Board had a number of departments like Aeronautical Production Board and so forth. And there were labor departments of the War Production Board and so forth. Got to a very interesting point in the moving of the manufacture of airplanes west of the Mississippi, I just gave you, absolutely overnight. And they moved into Wichita, Kansas, a city of 100,000, and within weeks, 200,000 people there. Everybody was sleeping in shifts, actually 3 shifts in beds. And they ran the moving picture all night long. It's 24-hour basis. So if you're on the 12 to 4 shifts, or was you go to movies at 6 in the morning, where it was. The place would run on a 24-hour basis, but extremely uncomfortable. There are a great many people then. This was on all these places they moved into in Oklahoma, so same kind of thing, but particularly Wichita, Kansas, which was the Boeing, the big B-29, the big bomber had to be done there, and it was very critical. So the War Production Board became very concerned because the people going to Wichita, war worker after war worker, went there, and they found conditions so uncomfortable, and they said the aeronautical world doesn't have any future after the war. Nobody could think anything like that. These airplanes are just for the war. And so we better get a job someplace else where things are a little more comfortable. So the quits began to exceed the hirings by laughing them out. To such an extent, they said we'd never be able to get our airplane program through. This became great consternation to War Manpower, to War Production Board, particularly aeronautical engineering. And so there was a labor section of the War Production Board. That's where Herman and Greg Bartecki were. And they told me that the labor unions were very interested in this situation. In the labor unions, the aeronauticals, these are it's called the that's mad at me. And the National Association of Machinists and Airspace Workers today, that's the full name. And the National Association of Machinists is the oldest union in America. They are really the original master craftsmen of the machine tools and so forth, real machinists. And so the Machinist Union said they would like to help about this production. They knew that this was really trouble because labor was leaving out. Therefore, everybody's saying to labor, what are you going to do about this? And the machinists said, we think something can be done. And they said, we have heard about Fuller has a house designed could only be produced in an aircraft plant. And maybe that would be something. This would mean then after the war you're going to need houses and not airplanes, so that we might be able to get to where these might be appropriate for an aircraft plant. And that seemed to appeal very much to all the people who were production were concerned. Grover Learning was head of the aeronautical production. He was a friend of mine. And so it was decided that it could be a good idea. So the labor union said, would you like to pick the very best labor union in Wichita, the one that we consider the fairest to labor and the most favorable to business, really trying to get things going and not really being obstructionary. So I said, of course. So the National Association of Machinists then picked out, because they were in all the factories out there, they picked Beech Aircraft. They said they have by far the best labor relations in Wichita, in Wichita. So I was asked then to go out with the labor men and the war manpower and the aeronautical people. We made a trip to Wichita for me to talk then to the vice president or operating manager of Beech Aircraft manager, Jack Gady. And I went over my design of the Dymax house, but the modification I had made of it by virtue of a great many changes in technology that had occurred since 1927. I've updated it very much to the design you saw there. And for the moment, it's still on the mast, but it's not up in the air, so you don't realize it's on the mast. Because there were various reasons I thought I'd have it either valid, have it either way. You could have it down or up for a garage. We wanted the garage or a hangar. Now, I showed this whole thing to Beech Aircraft. Jack Gady himself was a production engineering man, and a very, very astute, but also a very hard operator, executive, and he said, this really is suitable. He thought I might be an industrial designer, that I had something that's going to destiny. But he saw that I was really using aircraft technology, everything I had there was very suitable, and that he could see it could be really economical, so he was very game to go ahead and do something. The labor unions then had me go give a lecture at their labor headquarters to all the shop stewards of all the aircraft companies there, and they decided that this would be very, very favorable. They were all interested in housing. And I was really amazed at that labor, because they did not look at it in the way architectural aesthetic might be thought of in some cities. They really looked at it as a sailor would about a boat. They could see this kind of a boat would work. They knew their aircraft technology, they knew it, beautiful materials, and it's going to be very strong, and they said, that's great. So they were very much for it. So then the deal was made with Jack Gady, where I said, I will only do this then if you, Beech Aircraft, let me have top mechanics for floor. I don't need so many. You've got thousands of men employed here, but I'd like to have, he said, how many men? I think I asked for 8 of the very best mechanics he had, superb craftsmen, who would I then use for several months to do this job. And they were to loan us the tools from Beech Aircraft. It was to be under their auspices. They decided at first it was going to be on their factory. They then hired another building downtown. They decided it ought to be conducted, might be disrupting in the actual practice. But I did get these best mechanics. They said all the tools I need when I want big power brakes, whatever, they came right over and installed them. So this, you see what I really learned in lessons about this. Now it is a fascinating matter that having talked to all the shop stewards, within a week after this agreement was made, they had the curves there in Wichita, the aircraft, the quits over hiring, this thing just going off like that, people, and it stopped absolutely abruptly, went absolutely vertically like that, and went just exactly the other way. The hirings began to, so apparently it was just what the human beings there felt was really worthwhile living under the tough conditions in Wichita and so forth. And it was everything the World Manpower wanted. So World Manpower then said, they accredited my having anything I wanted. So then the Air Force gave us an order for two of these units to be used then for General's headquarters on Okinawa, some Pacific island, and because they'd have to be then subject to all the transporting and so forth. So under those auspices, then we went ahead and produced this structure. And when the war was over, the unions immediately said then to Beech Aircraft, all right, how about that house now? And at that point, many things began to go wrong, because then it turned out Beech Aircraft itself said, the local banks here, we're the only aircraft company that is, when the war came, the government didn't have to give us money and give us our tools. We were able to carry on our own. We've carried on for a fantastic number of years on our own, and the local banks have agreed to give us $10 million for tooling up our private plane business, and which was their fault. During the war, they made several things. Some of the bomber wings, but they made primarily the General's car, the Beech 14, which was a beautiful ship for that. You know, eight place, a General ship, and those are still going pretty strong. But so Beech said, the banks have given us, you need $10 million at least to tool up for that house. And Beech did go into a study. The production engineers costed it all out they put in they gave a firm written bid to produce this house, $1,800. But it had to be in lots not less than 20,000 a year. In other words, they looked for that curve of the all other I gave you about the automobile. This thing began at 20,000. The numbers of types of parts in an automobile is 5,000. This only had 328 types of parts, so you can understand why it could start lower than that automobile figure. 20,000, and you suddenly the all other costs are now leveled off with the cost per pound. So it did not have, however, the kitchens and that equipment in it. The General Electric then got up a deal where they would rent to the house a complete package of kitchens or both at a very favorable rate. I've forgotten what it was, but the yearly rate was so low it made the whole idea of living out very, very favorable. There were over 37,000 letters wanting to order one of the houses. The publicity was really unsolicited, and then suddenly began to go very fast, and this extraordinary overwhelming of orders, many with checks and so forth, but there was nobody to produce it. Beach didn't want to do it, and all kinds of exploiters came along, wanted to put up money, and they really were not the kind of people you like to do business with one way or another. And the next thing that happened was that there was no way to distribute. This thing was premature that way. I did try to warn people who were putting up money backing at the outset that there was no provision here to produce an end product for the delivery of it, the kind of equipment you're going to need, how to get this many installed properly and things like that. So that we found then the contractors who began to come and want to be distributors for it in various places. I did develop a truck, which you'll see in some of these pictures, for assembling my dome, and that could have been modified, but in order to pay for that truck, to keep it really paying for the distributor, he'd have to install several houses a day. It could do that, but that means then you had a whole lot of things to be taken care of, because there are all kinds of building laws, codes, but the most absolutely defeating fact was that the electricians and the plumbers have the absolute monopoly on turning on the juice to the city and the main supply, and they will not put it on. And they said, we're going to take all that plumbing apart, we're going to take all electricity apart. I had absolute beautiful harnesses like the airplane, and to just hook the whole thing up, but we're going to take all apart. All the really great savings were in trouble. So the project wounded up, and no, not bankruptcy, so forth, just didn't go anywhere. I'm very glad to say that the momentum, the government, a lot of people in the government, and a lot of money, I don't think it was really kind of political money, that wanted to back it, did then back, they got so educated in the idea that they backed the Lustron House. And the Reconstruction Finance Corporation finally put $30 million in the Lustron, and the whole thing flopped. Again, because the times had not really come. The older building industry, the old contractor, didn't like that feeling at all. It was, in many ways, it just always contradicted their interests, so that its time had not come. Now, I'm going to show you more. Now, this is just a model. Next picture, please. I talked to you yesterday about the aeronautical interception of the winds. Instead of having a windmill, you have a fan, but it has limited size. But this building then is going to interrupt an enormous amount of air, of the wind. So we went into studies with using the turnip-shaped great gas tanks out on the prairie there, the gasoline oil storage tanks. They're called the Horton spheroid form, which is going to be very much like this. And we were given permission to climb all over they had great ladders going up there, using long poles and streamers, many of them, able to get the aeronautical pattern of the air flowing around those big buildings, and taking anemometers at the different parts, we're finding it out in front of it, like the front of the bridge of a ship on a boat. There's places like the cigarettes out in front there. There's the least air motion. There's really a vacuum cone out in front where the airs are being opened up, they're being opened up, pulling apart, and absolutely still. But then as it goes around the shoulders, it gets up enormous velocity, and then airs have to come together again. So there depends to be great turbulence in the tails on something like that. You could see it on the from up top of the tank, and particularly when they got to have some snow, the tail goes down maybe sometimes as much as a mile. There's a very enormous drag on these buildings, and we found what these velocities were. One way or another, gradually began to study shapes of. I was getting about the umbrella, doing all these things. How could I then get the point where take all the air motions around the building and we find where the focus would be, and then have a ventilator that would rotate so it always, the opening of the ventilator would be exactly where the low pressure was trying to pull the air. And you see in this picture was a transparent model. We removed my figure in front of it. You're looking at a transparent one where the floors are double, and you can see how the airs were, if you pull the, there was a cylindrical mast inside that where you pull the air either from below the building right up throughout the house. There's a vacuum line on fastened to the vacuum to the ventilator on it right now, and you could pull the air over various circuits. So you could pull the air out of the double floor, which meant the air is being pulled out around the edge of your floor. So if you want to sweep or anything, the air is you just sweep to the edge, everything is taken away from you, and so forth. It was possible to get beautiful aeronautical controls all through the building. And then we would put a little smoke in these things and see exactly how these things would behave. We began to then develop wind tunnel tests where we had the building on a scale, so you take exactly what the drag was and so forth. And in front of the big Ventura wind tunnel, and then learning more about it, and we had the models hung upside down as they do inside the middle of the wind tunnel. We found what the drags on that building. We really were truly concentrating all the drag of this building at this one point. Next picture. Then we're looking here at these are all the parts for my building when it's finished. I designed them so no part was to weigh more than 10 pounds. Any part could be picked up by one man. Each part should go into place without anybody having to wait for somebody else to help to put it in. So you'd have one hand could handle it and the other part could fasten it into place. So they could work really quite fast. Everything was designed to be nested. So as you're looking there are down low there all those floor beams, beautiful aluminum floor beams where you're going to pull the air through and so forth. Those are all nesting one in the other. They weighed very, very little. And all the ceiling pieces, everything is there. Next picture. You see the boom coming from the truck that I developed to assemble them. And the boom is above the house. We got the mast up. The mast consisted of 7 stainless steel 22-foot long by 3-inch tubes, each tube weighing 10 pounds. Very light in your hand. You put it up like a billiard cue on the little button here, and then 7 of them are strapped together, and we had runners between them so they would not twist like a rope. And then as you put these straps on like that, there were cleats, so you could keep climbing the mast. You went on up with doing it. The hardware was very, very exciting with this job. So that the mast, a total 70-pound mast, and incredible carrying capacity. So there it is standing up. It's a very beautiful thing, and had a header on it, very much kind of things that get into racing sailing boats today, but it had all kinds of shears, ball-bearing shibs, and so forth. Because we then had a ring that's going to be put around the mast. You're going to lift it like an elevator, and from this ring we had what they call the rods. They were the aircraft chrome moly rods going out to what they call the A-ring, and the A-ring was just all screwed together like a fishing pole, and then there were diagonals going down to the B-ring, and sort of like a Japanese lantern form as it came down like this, and then finally to the C-ring. Then we went down, rods crisscross down to the floor ring. Now, what you're seeing there is the mast standing up, and up in this heading, there are all these ball bearings, and it had lovely shibs and little winch over here, so the cables would pull. There were 6 cables came down from the over ball bearing shibs to the ring, so this whole thing went up like a theater curtain. It was a lovely thing. And next picture now. Incidentally, the bottom ring is in place, and that is made out of magnesium. It's very light, large magnesium castings of what we call a Z section. Went like that, that way. And the inner lip then carried the inner floor. Everything rested on that. It was very, very stiff going like that, and obviously can nest. The Z can nest on the nest. The individual pieces were 12 feet long. The castings were about a ½ inch thick. It was a very powerful ring, but magnesium weighing relatively little. When this thing goes on up with then that ring was hanging there. Amazing thing happened, because if you take a diameter of 36 feet, so pi d, and you've got then about 110 feet long, this thing. Now, a beam 110 feet long like that, I would just kick this thing, and like rubber went around it. I never saw anything like it. Any one piece, you would swear nothing could budge that thing. I'm talking about metal this thick. And this section was 4 inches, 12 inches, 6 inches, very stiff, a ½ inch thick. You just couldn't. But to see what really happens when you get a big size, to see that you hit in a wave going around, there's an extraordinary thing. Of course, we stabilize that as you do with your wire wheel, of course, but I want you to realize very interesting experiences you have as you get into things like that. You never could dream of happening. Now, about then, the A ring's been put in place and the B ring's been in place. Those are also lovely. Those are stainless steel tubes. Very, very thin, weighed fantastically little. Next picture. Now they've been raised and the roof sheets have been put into place. Now the roof sheets, I had ribs, and these ribs are what they call a hat section. This is of sheet metal, and it was only 032, they call it. It's the thinnest where they make the thin skins of an airplane with. Hat section, you like that. And so there's a lovely channel on either side of the U. It's a very, very stiff affair. Then they have what they call a stretch press in the aircraft game. So I took these straight channels, these straight hat sections, which are very, very strong. Each one of those weighed just 2 pounds. They were 13 feet long. And the stretch press we had is a wooden form, and it has the hollowing out of the shape of the hat section, and then has the size of the wood or the size of there was this U channel on the size of the hat section. There are 2 great fists that take a hold of the ends of that hat section, and these 2 fists, the hydraulic arms move and pull it down over that wood and pull it in the exact shape of your curvature. Incredible, the stretch press. Lovely tools you find like that in the aircraft industry. We have some very beautiful pictures of that, and I really get to a point where I can't bring all the pictures in and never get through. But at any rate, those hat sections have been put up there between the A and the C ring. And then they are bolted at the top and they're bolted at the bottom. Then what they have then is the roof sheets are then just straight panels of aluminum cut triangularly, so you gain economy because you cut one triangle this way and that way. They're long gores. And they have a turn-up angle at the head and at the bottom, so that they're pulled very tightly by bolts over the frames. If you look at them, you see actually they're pulled this way. There's also a little secondary curvature. They get in hyperbolic, almost hyperbolic saddles. And they don't have to touch each other because between the two, I kept a deliberate space so that ice could melt between it. So, well, there's a deliberate space of about 1/8 of an inch between the edge of each sheet, because each one of them has been stretched over this hat section, which is a gutter. So any water just goes through the gutter and come down the bottom. And all the guttering, we had also on the inside an inner skin, so all the moistures of the building precipitate inside or the water outside, all came down to a built-in gutter that ran around just above the window section there. And that came down through pipes in the window section to an enormous gut at the bottom. All waters that landed on this building, either generated inside or outside. We caught it all went to assist it. Next picture, you'll see the whole roof. Suddenly, I told you that the little elevator went to work. It's like absolute beautiful theater. She went up like that. And then now all the cables are pulled taut, crisscross pairs of diamonds, and then we get in the plexiglass windows and so forth. Next pictures. Then there is a big ventilator. It's 18 feet in diameter. It is mounted. I used a Cadillac front wheel spindle bearing, which had very good bearings and so very good forging as the main spindle for it to sit on. And then we had, when it went around the 18-foot track, we had ball bearing rubber wheels that went around the track. Now all of this is mounted on a splining. A spline would slide this way like that. So my shaft for my top ventilator, which rotated like that, could slide upwardly on a shaft. It was designed so when we get tornadoes, one of the things that happen is immediate, incredible dropping down of the pressure. Atmospheric pressure incredibly dropped. And what happens, the buildings had air inside it, normal pressure, but suddenly the pressure is relieved outside, so the buildings explode. That's why you see so much lumber and everything in the sky. Everything explodes. So I had this on top of my building then now is designed so that if there's any big explosion or there is it would be a tornado. This is like the safety valve on a steam boiler. The whole thing just slides up. Immediately, it was good fun. I found I could then control the elevating of that from the living room. We could even let more air in. It was all screened so that it was beautiful for regulating, both pulling the airs over preferred circuits and taking care of the ventilation of the building. The aeronautical flows were under complete control. Now, you see the big ventilator being lifted on top. Next picture. Next picture, please. There was all very nice, really, designing of the window sills and the side walls below the window had little elevators, and the whole side wall would drop down like that below the windowsill. The aluminum went down like this, and it's all screened so that you could get any amount of ventilation you wanted below in it when you didn't open the window itself. The windows themselves were plexiglass, acrylic, double, because you're on a curve. Therefore, they were one cylinder inside the other. So a really very thin sheet putting in the cylindrical curve had enormous strength. So there was a little space just between the two, and acted like thermopane. So there's great, really incredible niceties in the design of this unit. All the parts came in that cylinder on the right. And we learned how then to do packing because there are all those parts. You saw them standing by the wall. But by having then a central shaft and jig shipping little arms sticking out of the central shaft, rotate around, you build all the parts into that, and then that slides into the cylinder. So, next picture, please. I'm sorry to say, this is the house then sat there in the building where the rent was very high. The beach had been paying. The beach didn't want to carry on about that anymore, and so the company, everything was broken up. Everybody was backing it because no production really was arranged, and so the company had not run out of money, but almost down to the end, didn't want to lose it, so that they simply disbanded the company, and this building was causing our rent so that the richest oil man in those parts, a man named Bill, whatever it is, Bill is a very hard trader, and like many rich people, and he said he would take it off their hands. He would pay them $1 rent to rent it off their hands and take the. We had 100% spare parts been built before the Air Force. So he said, "I'll let it back. Come anytime the company wants to, we just send it back to you, but I'll rent it for $1." So he went out to his oil lands outside of Wichita. He has Albany. He got a tractor. He borrowed a tractor. He wouldn't buy one, and he made himself a lake there, water, and he put up his house. But he used it most. He'd been told that the ventilator of the children would be sucked out of the house, so he took off the tail of that. He ruined all those things, and he built a great stone foundation. It was like mounting a DC-3 on concrete, and so it's never been anything so quite so incongruous. Anyway, he brought up his 6 children, and there the bathrooms worked and all that part worked, and it is still there. And but I say I feel quite badly about it. Went out with all the workmen from Beech Aircraft 2 years ago. We had a wonderful reunion there, and they looked over all the parts they had made. They were extraordinary men. My feeling with them was very much my feeling with you. I'm sure you begin to feel quite intimate with me. And we feel enormous camaraderie. The camaraderie of that group was something never to be forgotten. And they all still feel just as strong in that way. Most of them retired, but when they all came together, machinists brought them all together. It was really a great joy. Now, I'm just as confident as can be. One of the most beautiful things happened about this, my original estimate of the weight of the Dymaxion house, because this had the same 2 bedrooms, the same 2 bathrooms, the same living room. All the things were really the same, except that I didn't elevate it where you could have the garage. That wouldn't have made it any heavier anyway. We came out the same 3 tons that I'd figured for 1927, so nothing could have been really more fortifying to my confidence in my capability to design. But I'm really very confident we're going to see something of the Dymaxion house. But what I then did in my strategy, because I was so upset by the electrician business, because the electricians and the plumbers, I say, they are really merchants. They call themselves master plumber. They're not really of the laboring class, and they play a lot of tricks here. And they do have these licenses, and they play politics very, very heavily. So what I found was that the electrician and the plumbers will bring me an electric wire or water pipes out to an open field. I'm going to be a farmer. I might want to have some kind of spraying going on, but they'll bring it to an outdoor head. And so I said, right, and they will put the meter on it, then we'll hook it up. So I said, well, all right, we'll have to do that, and then I said, I see that the trailer business is starting, and I see that houseboats and all these things coming along. A lot of people are working on the mechanical package now. What has to go inside, I'm simply going to do the shell. And by doing then the proper shell, this brought me then to my realization, my experience that I had with the mast of the Wichita house. The real problem was for the big overturn of the winds. The stays had to be fairly far out, you can understand the angle of vantage. I found those stays bothered me coming in through as I had to allow for them going through the house. I found what I could do was simply make the mast itself a sphere. That I could get into the geodesics, therefore I wouldn't have to have interior masting. The mast itself simply swells up. It's just a truss mast, fat mast. And so I saw then if I began to then develop, and then what I could do, have the water and the electricity brought to a site. Then I bring my dome and put it there. And then you can drive your trailer in with a package, just a platform with all the machinery on it you want. I saw that this would be probably a way we could really get going and not really run this. So that became my strategy in going over completely to domes to that point. We're now up to 11 o'clock, and I think it would be a good time to stay off today. Tomorrow I do want to talk a lot about philosophy, but we have not shown, we have an enormous number of domes to show, and they have so much of the projects with students and the consideration of all the design science commitments that you really have to make, and how the students really learn about that I think those domes are really worth the showing. We find that we can extend over, Maddie will tell us a little about this, so that we have our Saturday, and the Saturday can be quite long. We realize we have many hours in it. And so that I would like then to get in those dome and the student projects tomorrow with you, because they do show so much. And they represent the beginning of the real breakthrough. Wichita was great, but really it had not happened yet. But the domes really began to happen, and they really became very much a part of the way the world is working today. And so it is interesting. The first ones to be really installed were the ones for the defense early warning system up in the head of Thule. I said way back in 27, one place I really got to start and really meet the conditions, and where there'd be no fence would be the Arctic. Sure enough, the first place my domes really ever went was the Arctic, in great numbers. It's interesting, I'm just going to give a finishing figure tonight. the Western Electric Company, who are the parts manufacturers for the Bell system and the telephone company. I'm sorry to say the federal government, I think, make a very great mistake right now. The antitrust is trying to break up the Western Electric that manufactures parts from the company who gives the service with the parts. At any rate, Western Electric had the contract to install the Defense Early Warning System, a fantastic contract. How many dual-line radomes there are, I guess it's still classified information, but there are a great many of them, ringing the Arctic from all the way from Scandinavia, across the Iceland, the Greenlands, and so forth, across all of northern Alaska, down the Canada and Alaska, down the Aleutians, and the Western Electric's operation. Most of this had to be in these extraordinary conditions of the ice, frozen ground, it's terrible stuff to work with anyway. Practically everything had to go by air. There's some things got up by ships when they got to having the northern passage, but the operation that Western Electric did in installing that under the adverse conditions of the Arctic, which is really terrific to operate. The logistics of it are very fascinating. The actual weight of materials moved, the foot-pounds of work they did was equivalent to what went into building the Great Wall of China. And the Great Wall of China, I think it was 300 years, and this was done in 3 years under those Arctic conditions. It was one of the most incredible operations of history. I don't know anything quite so formidable that's going to be taken such a big way and so superbly executed. To really try to break up then a Western Electric, my idea, the industry really counted, the ones that are the service industry, and you have to have the very deep cooperation between the Bell system and the Western Electric. I'd like to go on the witness stand and with the federal government, but most of the time I'm glad to be tacking big money, but I don't think of them as big money. The operation of the telephone company has always been really, it's set very mild. It's been a great deal owned by the people of the actual workers. It's been as reasonably mild as an enterprise could really be. It is an enterprise, and I think the consideration of the worker and everything has been absolutely phenomenal. I'm very severe critic of these things, and so I do like to have that built into our piece, that I hope they will not break up the very, to me, absolute essential intimacy, and from a design science viewpoint of the Western Electric and the Bell system. This is in Thule. This is the northern end of Greenland. It's almost up the North Pole. And it's just an incredible operation. I have one over the exact South Pole, which you'll see tomorrow. The exact South Pole. It's called Project Deep Freeze. It's a lovely dome. And this is a lovely dome. They have an eye dome on the side there. I think we'll then stop for tonight, and we'll get deeply into these tomorrow.